Hello, everyone. Let's start our today's class. I think first we're going to talk about the homework I have left to you guys last time, and then we'll move to the final section of this chapter. After we review the theorem of momentum of the system of particles, we will do some examples today. And if we still have time today, it is time for us to move to the new chapter, chapter 13. So first,
Good
let us
yeah,
see, is there any problem? What? Number 16, I'm sorry.
good morning, teacher.
Good morning. Can you guys hear my voice clearly?
Yeah.
Okay. Then I'll move on, okay? We're back to the homework we have left the last time. Let me read it first, then we'll do it together. So you guys can look at this picture. A disk of mass m1 with a rod of mass m2 hinged at the center rules on a plane. So you can find this figure. The radius of the disk is r, and the length of the rod is 2L. So at an instant of time, the rod has an angle theta relative to the vertical direction. We can see this angle here. And the velocity of the disk center is v, you know? So this point always has a horizontal velocity magnitude is v, right? And the angular velocity of the rod is omega. So omega is known. Determine the total momentum of the system. So before we try to finish this answer, to finish this problem, we should review what is momentum, right? Do you guys still remember? Actually, we have learned. So we give this concept from a single concept. Or if we have a single particle with the mass mi, right? If this particle have absolute velocity vi, so we have the definition. Its momentum for a single particle is p equal mi times vi, right? So p also is a vector because its direction is according to the direction of this particle's absolute velocity vi. So if we know for a single particle is momentum, then we have the concept about particles of system or a system of particles. So we will have P will equal sigma mi vi, right? Because maybe a system of particles, there are a lot of particles, right? Each particle has maybe I can write here it use pi to denote the momentum of a single particle, right? There are a lot of particles constitute a system of particles, right? So the total momentum of this system of particles will be sigma mi vi. And we also can write as if we use m to denote the total weight of this whole system of particles, and then we use this vc to denote its absolute velocity of its mass of center, right? Mass of center. So then we can find actually a system of particles. Its momentum can just use the total weight m times its mass of center absolute velocity. So back to this problem, we try to determine the total momentum of the system, but we find actually this figure, it is a system of bodies, right? It's a system body with two bodies actually. The one is the wheel, right? The one is the wheel. So, from the known quantities, we can find the radius. Actually, the wheel also is a disk, right? It has radius r. It has mass with m1. And we know its center is O, and is absolute velocity v, right? So maybe I can write this I directed to denote that actually this v is along the horizontal direction, right? And the second body is the rod. You know, the rod OA, it has a length with 2L. It has this is m1 and has the mass m second, right? And has and what angular velocity of the rod is omega. And actually, we know actually its center of mass will be the half length along OA. So here maybe just here is its center, right? So here we don't know its VC. We don't know its absolute velocity VC. So if we know this, it will be let us assume that we already know the VCE, then the answer will be P total will equal M1 V1, right? Plus M second VC, right? Then we'll finish this problem. So the thing is, we should try to find some method to find how to calculate VC here, right? So once again, please, you guys, we should analysis the motion type of OA, right? Let's see this rod OA. Can you guys figure out what kind of motion it had? Actually, it is a rigid body, right? We have learned a rigid body. It can be three types of motions. One is translational movement. Another may be rotation around the fixed axis or fixed point. And then the third one will be plane motion. So actually here, our body OA actually it have plane motion, right? Plane motion. So that is the most complicated motion of a rigid body. So we should use the pole method. Do you guys still remember? We should use the pole method to find the mass of center is absolute velocity VC, right? So it's very convenient for us to select the point O as the pole point. Do you guys still remember? Actually, what we want to find VC should equal VO, which is our pole, and plus VCO, right? You guys still remember this equation? Actually, how we use this pole method to find an arbitrary point on a body which has a plane motion, right? So maybe I should change my pen's color to let you guys clearly understand this. So I will change it to maybe purple. So you can see, actually, we are trying to find the absolute velocity of point C. So maybe we can draw here. So this VO, right? This VO actually is V and along the horizontal direction. So we can draw here with V. Another VCO, right? It should perpendicular to OC, right? And maybe along this direction, actually it's according to the omega. So here you guys can find, we know this omega before we do the calculation, and this omega with the CCW direction, right? So we can find actually. So VCO it must perpendicular to OC here and along this direction. So this is VCO, right? So so actually our absolute velocity of mass of center C will be VO plus VCO here. So if we have this angle is known, so if here is theta, so can you get understand actually this angle will be theta, right? Because this angle it have two slides, right? Each slide perpendicular to this angle's slide. So this one perpendicular to this one, and this horizontal one perpendicular to this vertical one. So these two angles will be the same, will equal, right? So we should find a very clear method to denote this absolute velocity that we see. So I can write as, so can you guys understand? We can write as VC equal, VCO. VCO actually is the relative velocity, this point C relative to point O. So you can think about if you are a Superman just sitting on this disk, you look at the point C, actually you will find actually this C has a fixed angular velocity, right? Just omega. So actually we know the magnitude VCO should equal omega times L. So this length is the half length of the total length of OA, and we know OA's length is 2L, right? So this OC is length is L. So VCO will equal omega times L. And here we are talking to these two components. So we can divide it. We can divide VC with two components. So one is along X our horizontal direction, another is along Y our vertical direction. So here we can write, so we have VO just V plus VCO times cosine theta. So we have omega L times cosine theta, right? And then we talk about its vertical components. So actually this way, it will have 0 components along the vertical direction because its direction actually perpendicular to this vertical line, right? So then we will have VCO, which is omega L times sine theta. So this component also along the positive direction of Y. So in the same manner, we can write this way as V equal V I, right? So you guess we can write as this P. So this is the whole momentum of this system. So we can write it two components also. So Px, right, will equal M1 V1x plus M second VCx, right? So we can write as M1V, right? This is V component, X component plus M second, and you can find its VCx in here. So we have V plus omega L cosine theta. And we also can write Py. It will equal M1 V1y plus M second VCy. And we know actually V1y will be 0, right? It only have horizontal components. So the first atom of this expression will be 0. So plus M second. We just use this omega L sine theta. So this is its Y components of P. So the final answer, I think maybe you can write as P equal PXI plus PYG. That's the final answer. So after my explanation here, can you guys understand that? Can you guys understand that? So I think the key in here, you guys should remember what we have learned, the pole method, how to find the second body OA, its mass of center is absolute velocity, right? If we find its absolute velocity, then the other steps is very easy to understand. So you guys, please, you guys can try to understand what I have explained today, right? Explained today and try to understanding this. So actually, it's quite easy, just from one particles concept to the system of particles, then the system of bodies. We should know that when we use concept, we always use its absolute velocity. So that's why we should find absolute velocity of mass of center of mass of this OA, right? So I hope you guys can totally understand this. If you cannot, maybe you can take your time to review this video again, because I think some gentlemen are recording our class today, right? So I think it's time for us to move on. This homework all about. So let's move on. I think today we're going to finish the theorem of motion of center of mass. Actually, this page we have mentioned the last time, but I think I'd better repeat a little bit because I think the whole chapter 12 is very hard for you guys to understand. So theorem of motion of the center of mass, in Chinese we can use that 质心运动定理. So I hope you guys can just try to understand why it is this, because I think everybody understand the second law of Newton's about a single particle, right? We have ma equal F. If we just use I to denote it is just a single particle, right? So actually here we are talking about a system of particles, right? It means a lot of particles that constitute particles. So we should use the method, maybe the same method. So using the momentum theorem of system of particles, because this is the momentum of a system of particles. So if we do the first derivative calculation, so dmvc dt should equal sigma FIE. So this E means all the external forces acting on this system of particles, right? So if the mass of the system does not change, it's always true, right? So use this capital letter M to denote the whole mass of the system, right? So we can write as this because we have AC equal what? dvc dt, right? So we can write as MAC equals sigma FIE. We also have this expression. Do you guys still remember? We just need a reference coordinate system. So here will be sigma mi ri, right? Sigma mi. So we only need two types of derivative calculation. We can find actually AC equal double dot RC, because each M will never change. So double dot only means RI double dot. So if our system of particles is a system of bodies, so this means we can just find this will be sigma mi and sigma mi ACI, right? So in some case, we can use this relationship to simplify our calculation, right? It all 1, 2, 3 all means the same, means the momentum theorem of a system of particles, right? And The formula above are the theorem of motion of the center of mass. The center of mass are the differential equations of the motion of the center of mass. The product of the acceleration of the center of mass of a system. And the mass of the whole system is equal to the geometric sum of all external forces acting on the system. The principal vector of the external forces system. So that means we can use this expression to find the relationship between the information of kinematics, or information of motion, and the forces acting on the system, right? Maybe if we know all the information of motion, we can use this relationship to find some value of the external forces. And the second, if we know all the external forces acting on the system, we can determine the system's motion information, right? So you guess we will find actually this theorem is quite useful. It's very useful for us to do some analysis. So we always use this projection form to change one vector equation into three scalar equations, right? So we have MACX, MACY, and MACZ. Actually, because most of the system we are going to tackle will be plane motion system, right? So in many cases, we just use two of them, just MACX, MACY. That is sigma Fi. So maybe we can just use sigma Fx to denote this for simplification, right? This is sigma Fy, and this is sigma Fz, right? So we also can find, if we know, if we know the mass of center of this system, let's say to denote, if we know it has a path of a fixed trajectory, so that means at each position, it's very easy for us to give it a tau and it's a n. Using what? Using natural coordinate system. So we can just use this. Actually, we also have b, right? So this is tau direction, and this is n direction. Our b equal tau cross products n. Because our acceleration of a particle of the mass center of the system only have two components along a tau and n respectively, there are no component or zero components along b. So we have this conclusion. So MAC tau will equal sigma, we can use sigma F tau, right? We also have MACN, because ACN always equal VC squared over rho, so we have this Fn. Another is because along this b direction, there are zero components of acceleration a. So this direction always be in the state of balanced, or in the state of equilibrium, right? So this projection forms of theorem of momentum for system of particles. And we can once again repeat the system of rigid bodies. How should how should we understand what is the system of rigid bodies? So what's the difference of a system of particles? So can you guys understand, or can you guys figure out what the difference of system of particles and the system of rigid bodies? I think I have repeated this answer many times, because do you know, actually every body, each body can be treated as a special case of system of particles, right? I mean, each body can be treated as a system of particles. So we can think about that a body, it constituted by a lot of particles, because a rigid body under the conception that it never changed its shape. How big the load acting on the body, it never have any deformation, right? So that means any two particles on this body will never change their distance. So here, if we are talking about system of rigid bodies, means there are a lot of bodies constitute a mechanism. You guys can remember. Mechanism means any two bodies on this mechanism will be connected by some type of constraints, right? So I think I have drawn this figure many times. It's quite typical. So we can draw like this. So we have OAB, and we have maybe four bodies. So one OA have a uniform angular velocity omega, another is AB. It will have plane motion on this plane. The third is slider, this slider. Maybe the fourth one will be the Earth's ground, right? So we will call that is crank a slider, because OA can rotate around point O with the 360 degree, and this AB will have a plane motion, and this letter B will always along the horizontal line or horizontal trajectory to move left and right. So it left most position and the rightmost position we can find and denote with the length. So use this as. So we have a lot of kind of making them on our engineering field. So here, when we talk about system of rigid bodies, means there are a lot of bodies. Each body can be treated as a system of particles. And this whole system of rigid bodies also can be treated as a system of particles. Can you guys understand what I'm trying to talk about? So that means denoting by the number i's body. Thank you, number 18. So number i's body are with mass mi and velocity vcm. We have this. Why this is right? Because all this actually we will have m to denote the whole weight of this mechanism, and AC means its mass of center. It's what? It's acceleration. Actually, it will equal mi ACI, right? Actually, I have read this expression on last page. Maybe I can write it again. So because we have RC equal sigma mi ri, right, over sigma mi. So let's see sigma mi. We just use the single m to denote this. So if we do the second 2 times derivative calculation, so this double dot and this will be double dot, right? So here will be AC. So we just use this to denote M. So we have MAC equals sigma MI, because each RI double dot will be ACI, right? So that's why this is the thing, because MAC equal sigma FIE. So that's why this is true, right? So that's why this is true. So you guys should remember that actually if you just select one body of this whole body system, it also can use this theorem. So let me give you an example. If we select this slider to be an object to be studied, so we should give its false analysis. Maybe it have its accepts. It will have some support reaction, and because it will have will be some FAB to pull this slider, try to let it move along the horizontal line. So if we see this plane is frictionless, there are no friction force. So out of the three forces, let's say this guy will have acceleration A, right? So we have this force analysis and its acceleration here, so we can use actually MA, because this is along horizontal, will be sigma fx, which will be, let's see, it's just a theta, right? So it will be FAB cosine theta. Why is positive? Because its projection onto this have the same direction of A. So it's positive or not, just according to its direction compared to the direction of A, right? So we also have AY, which actually is 0 because it's not jumping on the Y direction. So we have, it will sigma Y will equal Fn minus mg. You see, this also is the theorem of momentum for just one body, right? And this is the whole body system. So you guys should know this. Actually, today we are going to talk about maybe 2 or 3 examples to show you guys how to use this theorem to tackle some problem, right? So that explanation of this page. So let's read this paragraph. The theorem of motion of the center of mass, in English, to denote this is very complicated. We should use a lot of English words, but in Chinese, we can just use 质心运动定理. So that means you guys should better learn Chinese well, right? Because it can denote more information than the same number of English words. I think it's true, right? So the theorem of motion of the center of mass is an equivalent expression to the momentum theorem of a system. Let me repeat this. What this paragraph tries to explain, the theorem of motion of the center of mass is an equivalent expression to the momentum theorem of a system. Because we have learned this, because we have dp dt equals sigma fe, right? So that means because, so once again, because P means mvc, it is the momentum of a system of particles. So actually, when we do this again, we have d mvc dt. Actually, because m never change, we can just write here dvc dt actually is ac equals sigma f. That's why we have this conclusion. The theorem of motion of center of mass is this expression, and the momentum theorem of a system is this. So that means these two guesses are equivalent, right? Being similar in form to the differential equations of motion for one particle. So these two equations are equivalent and are similar in form to the differential equations of motion for one particle, right? That's true. For a system of particles in arbitrary motion, the center of mass of the system moves as if maybe it's more like it would be a particle of mass equal to the mass of the whole system, to which all the external forces acting on the same are applied. So try to understand the whole paragraph. So here we also should talk about the conservation law of motion of the center of mass. So here, once again, I'll show you that the conservation law means 守恒定律. It's easy to understand, right? So we can explain this again. So if, if this condition is true, if this condition is fulfilled, if sigma fi equals 0, let me write this this MAC equal sigma fi e, right? That is theorem of mass of center, right? So if sigma fi equals 0, that means this guy will also be 0. And if this 0, because M never be 0, it only means AC, which equal what? dVc dt equal 0. Then it means Vc should be a constant vector, right? Constant vector means its magnitude and the direction will never change at different time moment. See, that's the conservation law about, right? Of the motion of center of mass, right? And if we see 0 equal 0, means when t equals 0, the whole system on rest, stationary. So that means our Vc equals C will equal 0, right? And so if at the time begin, the whole system is on rest, is stationary. So that means Vc, which also equal drc dt equal 0. Then it will deduce to this. Our position vector of the center of mass of this system will be a constant vector, right? Do you guys still remember what we have talked about the example last time? We have a big triangle and a smaller one, and it from this hair position move to the bottom position. We talk about why the big one will back to the left a little bit. Why? Because it should keep xc1 equal xc2. So that means that from the conservation law of the motion of the center of mass, So please, you guys should understand this. And if we only fulfill this condition along some direction, let's say it's x direction or any arbitrary direction, because we can place our x direction on any direction just for our convenience. So that means ACX will be 0, so VCX will be 0, right? So this is the same thing. This is the same thing. We also have example. We have maybe we have a ship here. It's floating on water. We ignore the so if we have a person here, so at the first time at start, the whole system is stationary. So if this guy from the left side to move to the right side, then this shape will move to left a little bit. Why? It should keep this xc. So at this, we have xc1, and when this guy walk onto the other side of the ship, then we have FC second, and these two positions will always be true along a same coordinate system, right? Actually, we have talked about these kind of examples. Do you guys still remember? So actually, that is application of conservation law, right? It is the application of conservation law. And the finally is the theorem of motion of the center of mass may solve two types of dynamical problems. So the one is knowing the motion of the center of mass. So maybe I should write this expression again. Sigma F. So the one is we knowing the motion of the center of mass of the system. So we know AC. Then we can determine the external forces acting on the system, including the reaction of constraint. You know, if we know AC, we can find out the maybe external forces acting on the system, right? So this is the first kind of problem. The second is we knowing the external forces acting on the system. That means this time we know sigma F, right? So this time we know the sigma F. If we know sigma F, then we can find AC should equal sigma F over M. Then we can determine the law of motion of the center of mass. See? So that is the two types of dynamical problem. We can call that 动力学问题. Dynamical problems, 动力学问题, just use this so-called the theorem of motion of the center of mass. Then we are going to talk about some examples, so you guys can try to pay attention to my explanation and try to understand. I think that's a little bit difficult for you guys to understand. So maybe we should, I will introduce this problem to you guys first, then maybe we should do some, have a short break. Then we'll continue to finish this example. So please, you guys look at this picture. A motor body is mounted on a horizontal foundation. You know, we have a horizontal foundation that is Earth's ground, right? It's never changed, Earth's ground. So the mass of the rotor, I think in Chinese it means 转子. So what is 转? Means it can rotate with some speed around some axis, right? It will have motion. So the mass of the rotor is m second, right? And the mass of the stator, you know, so I think stator means 定子, means here the body will never change, but it have a mass with m1. So the shaft of the rotor passes through the center of mass O1. So what is this sentence mean? It means the rotor it have mass m2 or m second. It will have a rotation around the axis which passes through the center of mass O1, right? So that means this means the rotor it have m second. It will have rotation around point or axis O1 along this direction, which is CCW. Its magnitude will be omega. So, but there is a distance E from center of mass O second of the rotor to O1. So this means the length of O1 to O second. Due to an inaccuracy in the production. Production here means manufacturing or fabrication. So when they made this whole system, maybe they are inaccuracy. So in many cases, this E is very small, maybe just 5 millimeters, you know? It's very small value, but when the omega is high enough, it will have very worse forces. So we are going to try to analysis this. So let us determine the reaction forces of the constraint exerted on the mount of the motor by the foundation when the rotor is rotating with the angular velocity omega, right? So I think to remind you guys, here we should find the reaction forces. But before we do this, we should give the assumption of reaction forces here. So do you guys still remember at the first part statics of this course, we have learned the 5 common types of constraint, because different type of constraint will have different type of reaction forces. So this is fixed. So we have learned that that kind of fixed. So if we have a rod, it's fixed here. We call that this kind of constraint is a fixed constraint. It's fixed here, it's never changed. So it has 0 freedom, right? So it cannot move along X direction. It cannot move along Y direction. It also cannot rotate around some axis. So it's more like this. So we have a lot of screw, bolt. Do you know bolt? 螺栓. It will fix this foundation into earth's ground. So maybe if you guys look downward, maybe you can find actually there are at least 4 bolts which fixed this foundation, green foundation, onto or into the earth's ground. So it can be treated as a fixed support, right? So we can draw its 3 reaction forces here. That is an X and Y and reaction M, which will restricted that this whole system cannot rotate, right? So that is fixed support. So this kind of constraint will have 3 reaction forces, but here we only can find an X and Y. We cannot find M until now. Maybe we can find M when we finish our study chapter 13, right? At that time, we will find actually we will have another theorem, which is let me show you guys how to write as this. We have dl0 dt will equal sigma m0 f. So the moment of momentum to fix the point, it derivative, one of the derivative calculation will be equal all the external forces, its moment to the same point. So we will learn this theorem at next chapter, chapter 13. So today we are going to talk about how to use what we have learned, the theorem of mass center to find an X and an Y. So I have finished the introduction of this whole system, whole problem, and it is time for us to have a short break. We'll restart at 11:10. So please, all you guys have a short break. Okay? Okay, let's continue. Our time is up. Let's try to use what we have learned this theorem to find the answer. Determine the reaction forces of the constraint exerted on the amount of motion, right? So let's So please, you guys try to follow me and try to understand what I'm talking about. So our solution have some steps. One is, we should choose the motor as the system of particles. We choose this motor. This motor in China we call that 电动机, right? It's 电动机. Choose the motor as the system of particles to be investigated, and the analysis of forces is shown in the figure. So we have these three kind of reaction forces, and X and Y and M here. We also have active forces with M2G here, right? Actually, it's a gravitational force because of the Earth, and M1G. There are no other action forces, right? So after we select the object to be studied and finish the analysis of forces, so here's the final result. And the second step is analysis of motion. So actually, here is one method we have mentioned. Actually, we can think about that. This system also is a system of bodies with two bodies. One is O1, right? And another is O2. So here it means our MAC, right? So M means the whole weight of the system. Also equal what? M1A1 plus M2A2, right? So that's why it gives this conclusion. The acceleration A1 at the center of mass of the stator, because the stator never changes its position. It's stationary, so its A1 will always 0, right? So the stator O1 is 0. So that means we only have M2A2 here, right? Why? Because A1 will always 0, right? So that is the reason. And the acceleration A2 at the center of mass of the rotor O2 is here. Because we assume that this omega is uniform, omega is constant. So if you just look at here, this O2, it has mass M2, and it only have, because its motion is rotation around the point O1 with uniform or constant angular velocity omega. So it will only, a second will be 0, I think. Maybe I read like this, you guys will know. So actually it should equal AT along tau direction and AN along A direction. But here omega is constant because we have learned AT should equal R alpha. Alpha is the angular acceleration because omega is constant. So alpha is 0. So here it's 0. So AN is only omega squared times R, right? Here, R actually is the distance from O1 to O2, so it's E. So this is omega squared E. So that's why they tell us the acceleration A2 at the center of mass of the rotor O2 is omega squared E. Its direction is always directed to O1, right? Pointed to O1 along this direction, right? This is a second. So if we know that, we can find, let's see this, because it's CCW direction, let's see this angle phi equal omega t, right? So we can find A2x will omega squared cosine omega t, right? But its direction is, if here is phi equal omega, we have another added line here. So our A2 can be projected onto this x-axis, but it will along the negative direction of x. So we have a minus sign. So A2x will minus omega squared e cosine phi, because phi equal omega t. So we have this, right? And A2y will equal omega squared e sine phi, which also along the negative direction of y. So also have another minus sign. So after this, we can use the theorem of the mass of center. Let's move to the next page. So according to the theorem of motion of the center of mass, we have, right? We have this. But this system is very simple. So sigma mi ACIX only have one atom. So we have M2 A2X equal Fx. So actually, maybe I can write here. So M2 A2X equal minus M2 E omega squared cosine omega t. Here we cannot see this clearly. Will equal what? Sigma Fx, which will equal what? Because along the horizontal line, we only have this nx, right? This nx. And we have M2A2y, which is minus M2 E omega squared sine omega t, will equal Fy. Then, but along y direction, we have ny minus M1g minus M2g, right? That's how we use this theorem of motion of the center of mass, right? So we can find that actually, actually nx just equal minus m2 e squared cosine omega t, and ny will equal m1g plus m2g minus m2 e omega squared sine omega t. So so let's do another analysis. So we find the dynamic reaction caused by the deviation from the center is periodic function of time. Why? So nx actually is according to this cosine omega t. Let me do some analysis for you guys. If when t equals 0, so omega equals 0, right? Because the whole system at rest, then nx will equal 0. And ny, because omega equals 0, so this atom will be 0. And y will only be m1g plus m2g. That means if the system is in a state unrest, right? Unrest, stationary, right? So nx will always be 0, and ay just is the weight of m1 plus m2, right? When there have an omega here, so nx will be this, and ny will be this, and you can find actually because it have cosine omega t and sine omega t, and both these two will be because cosine omega t, it will less than 1 or greater than minus 1. This sine omega t also is less than 1 and greater than minus 1. So that means if this omega is high enough, the higher the omega's value is, the harmful of this nx and this ny will be, right? And its direction will be changed. If this omega is bigger enough, so this part may be neglected. So the sign will totally according to the omega t. So sometime ny will be upward direction and sometime will be downward direction. The nx is also maybe directed right, also may be directed left. So this will very helpful to the foundation. So if you cannot check it with a period of time, maybe this boat will be wrecked and some bad thing happened, right? So that's how we use the theorem of motion of center of mass to find an x and an y. Here, I'd like to talk to you guys another method. So let us do this again, but we'll just use another method. I'll tell you guys how to finish that. Let's see. So actually, we also can use dp dt equals sigma f. And we have dpx dt equals sigma x. We have dpy dt equal sigma y. That means we do not use the theorem of motion of center of mass. We just use the theorem of momentum of the system of particles. So see, once again, we try to write this P. So actually we can find actually the whole system only have this. If this O2, it have this omega angular velocity, actually its direction will be here, right? V will equal omega E, right? Along this direction. Let's say if this angle is phi, which we know phi equal omega t, actually the rotation function of this rotor, right? And we can draw a the line, a dashed line, which is perpendicular to the direction of x, right? So you guys can find actually this also is phi, right? And here we'd like to use this angle, which is theta. So we can find actually theta plus phi equal 90 degrees or half pi, right? So you guys can find if we along this direction, so our P actually is our P equal mv equal m omega e, right? So actually this also we can find our P equal m omega e. So at this figure, we can find, I just find the blank area to write here. So please, you guys try to follow me, try to understand what I'm talking about. So we can find actually px, you know, px equal p times cosine theta, but cosine theta actually is sine phi because theta plus phi equal half pi. So means, but this part, this p projection onto this will along the negative direction of x. So we have minus sine and p times cosine theta actually is sine phi, and sine phi is sine omega t. So that means px equal m omega e, m omega e. So here m should be its mass, so we should use m2, right? m2 omega e sine omega t. And our py also should, you know, py times sine theta, but this is positive, so we have p is m2 omega e sine theta actually should be cosine. Sine theta actually should be cosine omega t, right? Cosine omega t. Let me check it again. Px, this is Px, and this is Py, right? This is Py. So we can use dpx dt sigma x. So we have, right? dpx dt equal what? Equal this minus m2 omega e. Sine omega t, its derivative will be cosine omega t times omega. So another omega here will be omega squared, right? Can you guys understand me? So dpxct will be minus m2 omega e cosine omega t times omega. And this guy will equal sigma fx. So this is nx. See, you guys can find the same answer is nx equal minus m2 e omega squared cosine omega t. And again, our dpy dt, so dpy dt, our py here, so we have m never change omega e, but cosine omega t, its derivative will be minus sine omega t times omega. So we have omega squared also, right? It should equal sigma fy, which will be ny. So because ny direction is a positive direction, and m1g and m2g is negative direction, minus m1g minus m2g. So once again, you guys can find the same answer, ny equal m1g plus m2g minus m2e omega squared sine omega t. See, can you guys find actually the same problem? We use two theorem. That means in essence, actually these two theorem is the same, is equivalent, right? So you guys can think about this again. Actually, we use the two methods to find the same answer, right? So this is one example we have talk about today. Let's see another thing. Actually, this is another homework. I hope you guys can finish. But I think we better talk about it together because it's a little bit difficult for you guys to finish by yourself. So let us do this together. So let me, actually it is a problem from our textbook. You guys can find this question and this figure from our textbook. So let me show you guys and try to finish together. As shown in this figure, the bar OA, the bar OA of weight P, right? This is weight P, and length 2L is hinged, it's hinged means this is the hinge. So at O to sitting. So this is sitting. At an instant of time, it forms an angle phi relative to the horizontal direction. And that means actually this omega is along CW direction. Maybe it have the same direction of angular acceleration. So I have told you guys before, maybe sometimes we use this epsilon to denote, maybe sometimes we use alpha to denote the same thing, angular velocity, So it tells us at some instant of time, it forms an angle relative to the horizontal direction, and its angular velocity and angular acceleration are omega, this is known, epsilon is known. So determine the constraint forces at the joint O, right? Because that is a hinge. Do you guys still remember? If we do is a force analysis, we should think about we remove this constraint, but we use its reaction forces to denote its action from this ceiling to the bar OA. Actually, it should have FOX, right? And FOY. We had talked about this a lot of time in the first part, statics, we have learned, right? So because of the type of constraint, it will have these two kind of reactions. So that is determine the constraint forces at the joint O. So how can we find our solution? So how can we find the value of FOX and FOY? Because we have the theorem of mass of center, we have MAC equal sigma F, right? So here we can use its projection form. We have MACX sigma Fx. We have MACY equal sigma Fy, right? So here we can find if we, because sigma Fx will only hit FOX, and sigma Fy you can find it just FOY minus P, right? So because P is known, so if we try to finish this problem, well, the only thing is how to find ACX and ACY. So maybe I should change another color. So we have to use what we have learned, some knowledge points from the middle part of this course, the motion analysis, right? So actually this OA is the rigid body which have rotation around the fixed point O, right? So here point C is mass of center. So we should try to find ACX and ACY. And here we can find actually AC because we know the direction of omega and direction of epsilon. So it will right at this ACT and this ACN, right? Actually, we can write at AC as what? ACT along tau direction plus ACN along N direction. And ACT should equal the length of AC times epsilon, right? So that is L times epsilon. Its direction is the same direction of epsilon. So this is ACT. And this tau, and ACN will be omega squared times L along N direction. So we should use this ACT and this ACN to find ACX and ACY. So we should draw some added lines. So let me, through the point C, draw a horizontal added line here. So we can find if this angle is phi. So this also will be an angle of phi. So you guys can find actually what we try to find is ACX. You know, ACX will equal because we can project this ACT onto this, right? So ACT, let me see this theta. So once again, we have this relationship at theta plus phi equal half pi. So ACX will equal ACT, you know, please see this picture, ACT times cosine theta. But this projection component will along the negative direction of x. So it will be minus direction. And here we have ACN. It also have ACN times cosine phi, also point to negative direction. So we have minus ACN cosine phi. So we should try to give the final result because minus ACT equal L epsilon. And the cosine theta, because theta plus phi equal half pi. So cosine theta actually equals sine phi. And here ACN should equal omega squared L cosine phi. Okay. Here we finish to find ACX. Then we should use the same manner to find ACY. So ACY, once again, so ACY should equal ACT times sine theta, which will along the negative direction of y. So we have minus ACT times sine theta. And we also have this direction. And here we should ACN times sine phi. But this time, this projection onto y-axis will along the positive direction. So we should plus, not minus, ACN sine phi. So once again, we should change minus ACT with L epsilon sine theta can be right at cosine phi plus ACN equals omega squared L sine phi, also is sine phi. See? From this method, we find ACX and ACY. Then we can use these two equations to find FOY and FO. Here should FOX, FOY respectively. So here we have MACX equal FOX. So we can find our FOX equal M minus sign replaced here with what? Maybe L can be out of the brace, ML. Then we have epsilon sine phi plus omega squared cosine phi. Right? And we have this MACY equal FOY minus P. So we can find actually FOY equal P plus this one. We also can have this M L omega squared sine phi plus, and not plus, I'm sorry. It should be minus, right? Should be minus. So it should be minus epsilon cosine phi. See? That's the whole steps how we find the final answer. I hope you guys can understand this. Actually, it just need you guys know how to find. We have a body which have known motion information with angular velocity omega and angular acceleration epsilon, the mass of this rod, the length of this rod. So you have to use this to find, right? You have to use this theorem of center of mass to find the reaction force FOX and FOY here. So actually this homework from the, I told you guys from, I think from engineer mechanical 2020. The girl's name is Rila, you know? Actually, it very clearly right on the paper, but there's something it's not correct. So actually, I have used this the same thing, right? So I hope you guys can understand. Maybe if you like, you can do it by yourself again, right? And the final one of today is this problem. Maybe after this problem, we will finish today's class. Next time we'll change to chapter 13. So you guys, let me show you this problem. We have a wheel of mass m1. You know, we have a wheel of mass m1 is hinged to the ground at a point A. You know, we have a fixed hinge here, right? Or fixed pin. So hinge maybe is a fixed pin. Whose outer and inner radius is capital R and little r. So it means here is R and here the capital R and letter little r, right? Respectively. A block B of mass M2 is attached to the inner wheel by a string. No, by a string. And this is a block with mass M3. Rests on a frictionless plane inclined at angle theta and attached to the outer wheel by a string. So this is M3, and we have a block of B. It have M2, right? It's attached to the inner wheel by a string. Block C of mass M3 rests on the frictionless plane inclined at an angle theta and attached to the outer wheel by a string. At an instant t, the block B had a downward acceleration A, right? Means let us determine the constraint forces at hinge A. So at one glimpse, maybe you guys will find it's too complicated. We don't have any idea how to find the answer, but we can do this by analysis step by step. You see? So here you guys can find we think or we assume that this string will never change its length, right? So since this is the wheel with the bigger radius and little radius, that means it will have the same omega, right? Have the same acceleration alpha. Because this one and this one are fixed together, it always rotate together. So we can find a point here. Let's see, this point on the wheel have V prime, and let's see it have along this direction have V3 because it matches V3 and A3. Right? And this one, let's say it had A, also had the direction V. So let us try to find, let's say we have a point V prime here, V double prime here. So please, you guys follow me. We first try to find its relation. So we have actually our V3 here, because it's connected with the string. So our V3 will be equal V prime. And this point actually is the point on a body which have a rotation around the fixed point or axis. So it will be equal omega times r. So what we can find, so that means V3 equal omega r. So we can find if we derivative with respect to time t from both sides of this and this, we'll easily find actually its acceleration A3 will equal alpha r, right? This is a very important relationship we should know before we do analysis, right? And we also, the same reason, if this downward velocity v, it also equal this point with double prime. So it should equal with double prime, which have the same angular velocity, but different radius r, right? So that means our velocity a will equal what? Alpha r. So this is another very important relationship too here, right? And after we do this, I will change the color of my pen and try to do the force analysis. The first one is this. So let's see if we just select B as an object to be studied. So it will have its weight with m2g, and it will have a ft. Actually, it has acceleration a here. So because its motion is simple, it's just is a what? A translational movement. So we can use a very similar Newton second law of Newton's, right? So we have along this direction we have m2a fm2g minus ft, right? So we can find actually, we find ft equal what? Equal what? Ft equal m2g minus m2a, right? We just move its position from this guy from right to left became positive. So ft equal mi m2g minus m2a. And once again, we should do this. So you see, we can find this one because it will have another ft1. Let's say ft1 by this string, and it will have its weight m3g, and it also have a fn. But along this direction, which is parallel to the slope, it have a 3, right? So we only need to give expression along this. So we have m3 a3 will equal what? ft1, right? Minus what? So if this theta, this angle always theta, m3 cosine theta along this direction, so m3 sine theta, m3d sine theta. So from this, you can find actually, you can find ft1 equal m3a3 plus m3g sine theta. See, after all this analysis, we can cut this. So this from action and reaction force ft1 here. We also cut this off. We have this ft here. And we try to remove this fixed pin and replace it with two actions is fax and fay, right? So after we finish this force analysis, we can once again to use the theorem of mass of center, because this wheel is fixed here, is hinged here. The wheel can rotate around the point A, but this point A will never change its position. That means AA always equal 0. That means AAX equals 0 and AAY equals 0. So until now, can you guys find how we can find it? Because actually A can be right as so here, maybe I should change another color again. Let me change it into, let's see, green color. So you can find, we can use M to G plus, because we have the important relationship here. So minus M2, we use alpha gamma R to replace A. So alpha R. And here we also can write as M3. A3 can be write as alpha capital R minus, plus M3 G sine theta. So here we can use theorem of mass epicenter with this field. So we can use, because it has mass M1, so M1 AX, which is 0, will be sigma Fx, right? So we should tackle it carefully, because this is 0, right? Because this is 0, but we should find, we have ft here, so maybe we need a line. This is theta, so this is theta. So you guys can find actually sigma Fx equal Fax, because this ft1 cosine theta along the positive, not positive, negative direction of x. So minus ft1 cosine theta equals 0, right? So we can find actually Fax actually equal ft1 cosine theta. So we can just replace ft1 with this, right? With this is ft1. So it will be cosine theta and brace m3 alpha r plus m3 g sine theta. So you guys can try to replace m3 here. So maybe I can write, because we only can m3 cosine theta alpha r plus g sine theta, right? So we only have one Fey. So once again, we can use M1 AAY should equal Fay equal 0, right? So we should analysis sigma Fay, which will equal, from the false analysis here, will be Fay minus its own weight, right? Because this is M1, I'm sorry, it also should be M1G. So Fey minus M1G. And here you should consider this Ft also minus Ft equals 0. So you guys will find Fey will equal M1G plus Ft, but we have Ft here. So plus M2G and minus M2 alpha gamma. I think this is quite complicated. I hope you guys can understand, but maybe it's too tough for you guys. Actually, I have a detailed analysis here. Maybe you guys can take your time to look this again, right? So this is the whole process here, right? So this is the important relationship between this point and this point. and this point and this point. That's how we find the relationship. You just see from what we have read on the page, right? And this the force analysis, which is very very important here. So for this, because it's have acceleration a along this direction, so you can write as this. Maybe this A1 is not the same from what I have finished today, but the principle is the same, right? The principle is the same. Here we use FT2 to denote this force. So we have M2A equal M2G minus FT2, and here is the force analysis. So I think that's all for this whole chapter 12, you know. Here we finish this chapter 12. Today we have a homework. Actually, it's totally up to you guys. If you like, you can finish, you can do this again by yourself. If you do not like to finish this again, it's okay, right? And that's all for today, and that's all for to chapter 12. Next time, we'll begin to learn chapter 13, right? I think this part, dynamics, is very hard for you guys to understand. So please, if you guys have time, please, you can read the textbook before my class begin, right? And I think that's all for today. Bye bye, all you guys. Bye bye.
拜
拜拜，
拜，
老师，
好的，再见，
再见，老师。
再见，拜拜。I'll close.